And thank you everyone for attending our first Friday noon talk of 2023. Today we have the great pleasure of welcoming Dr. Martin Vallieres. He is an assistant professor in the Department of Computer Science at the Université de Sherbrooke and a Canada CIFAR AI chair since April 2020. He did his MSc and PhD in medical physics at McGill University in 2017 and completed postdoctoral training in France and the USA shortly thereafter. And he is well known as an expert in the field of radiomics and machine learning in oncology. And I also like to say that Martin was one of my classmates in the MPU program, and he's off doing great things. So I'm very glad that he's here to talk to us today about his academic journey. So please, Martin, take it away.
Thank you, Pete. Thank you for the introduction. Thank you for the invitation also. It's a great pleasure to be here. Come back, at least virtually, at the MPU, at this place where I had so much fun for almost 7 years. I'll try to summarize this academic journey of mine and explain a little bit better what that title means. I hope it's going to be more clear at the end of this talk. So let's go. I'll dive into it. By stating directly the objectives of this talk, I want to share with you, as stated in the title, my academic journey as a MPU alumni, present my research activities since my graduate studies at the MPU up to my new position in Sherbrooke. So present that so you can know me better. And actually it gave me the opportunity, I believe, to reflect a bit of myself and think about where I'm going. So thanks for giving me this opportunity. Before diving into the main subject of the talk, I want to explain this concept because it's going to come back a couple of times during this talk. I'll use it quite a lot, actually, to try to explain what I've been doing and where I'm going. So on December 20 of last year, I saw this interesting blog post from Tejas Pandya, basically stating loud and clear that in academia, we need two types of researchers, divers and surfers. So what are divers and surfers? First, when we do research, we have a given research subject. That's a spot in the ocean, let's say the ocean of research. So we choose a research subject and we do research. We can do research by diving or by surfing. So diving, maybe it's what we think of the traditional research where we become experts in one specific subject, let's say. So I represent that here with a theta, okay, a theta of 90 degrees, where you really dive into the water and you do deep research in one subject. The drawback is that it's maybe in a narrow space in the ocean. You become really experts in one research spot in the ocean of research. Whereas surfing research, where you can think about that with a smaller theta, so theta of, let's say, of 0 for surfing, where you explore different spots in the oceans. You have a broad view of the ocean, and you try to connect the spots in the ocean, the research objects that you investigate. The drawback then is that you cannot dive or go as deep as you probably would like to do in each spots in the ocean, in each research subject. So there's this diving versus surfing research concept that I think we need to reflect on. What is interdisciplinary research in this context? What theta is it? And basically, also here I'm presenting the diving or surfing for just one individual. But if you combine in a network, for example, multiple divers, what is the ultimate theta? That's another. We could think about this concept for a while here. We can think about also, is there a notion for let's say computer science, and then a notion for clinical science, and how when these two combine. So there's different views about all of this, but let's keep it simple for now. There's a theta. Theta of 90 degrees is for diving. Theta of 0 degrees is for surfing. And there's obviously thetas in between. You can be surfing a little bit and then diving from time to time into different research subjects and trying to combine these research subjects together. So that's the concept of this theta that I'm going to talk about. And along these lines, there was another blog post that I read a couple of days after that made me think about diving and surfing, and that actually made me think, and I guess community may be reflecting on that now. Do we have the wrong balance of divers versus surfers in academia? So there was one paper in Nature published, and there was one blog post analyzing that Nature paper, basically stating and basically commenting on this figure here, where the authors developed a disruptive index. Okay, disruptive index about the different papers that were published, how many of them were disruptive for a given field. And what we see in this figure is that over time, based on their metric, and we would have to go deeper into the paper to fully understand what's going on and the whys and what we can do. But basically, the authors state that over the years since the 1950s, the disruptiveness of our research is falling. And another blog post from a couple of days later, one interpretation of one person here is that, so it seems that the growth in publishing, so quantity of papers, because the number of papers have really exploded, I find, in the last decades, the growth in publishing leads to narrow research. So maybe we have a lot more divers than we think, and maybe too many divers. So scientists may have just got stuck in their own narrow subfields. So this advocates for having probably a larger number of surfers in academia. And I kind of agree with all of this. We need to have the right balance of diving and surfing is as important as diving in research. So that being said, that's going to help me to explain to you the main body of my talk. My academic journey, research activities I'm doing at in Sherbrooke, and some other networks with which I collaborate. Let's start with this part, my academic journey, so that you understand a bit better where I come from. So, as Pete stated, I had a lot of fun in these years, really learning to be an expert in one subject, which was here radiomics and machine learning applied to oncology, where I did my master's and PhD here at the MPU of McGill. And I think, well, this number is an estimate, let's say, but I guess during these days, I was kind of a 80-degree type of researcher, more diving than surfing, because I got more expert in one or two different subjects that I combined, radiomics and machine learning. For example, radiomics, extracting quantitative imaging features from medical images, for example, PET or MRI, extracting these useful features, combining them with machine learning models to do predictive modeling. Here, predictive modeling, for example, one study we had done was predicting if a patient was more likely to develop lung metastases in sarcoma cancer. So ending up with a predictive model based on radiomic features, quantitative imaging features. So that's basically the summary, I guess, of my days at the MPU, or this research I did during my master's and PhD. During my postdocs, I did in Brest in France and San Francisco in USA. I kind of, I guess, began to be able to surf a little more. So let's estimate, for example, theta of 60, just a little bit more, still in the applied domain of oncology, but trying to integrate more and more different types of data together, and really getting into the domain of big data as well. So, for example, I won't talk too much about this paper, but it could summarize well the postdoc journey here, where we used applied AI, we applied artificial intelligence, and integrated different types of data, longitudinal data from electronic health records, so from different data sources. This was in San Francisco, actually, different data sources in San Francisco, and use that to do real world data. Sorry, not real world data, continuous pan-cancer prognostication. So that kind of summarizes a little bit. Still, I would say diving quite a bit into building predictive models for cancer, but being a bit more of a surfer, applying these models for different types of cancers and with different types of data. That was the postdoc part. Now, in Sherbrooke, as an assistant professor, I think I'm going more and more to on the surfing side, and that's just an estimate. But let's have as a just for the view here. Let's say it's theta 20 degrees, and I'll try to explain a little bit more. Obviously, this theta in this talk, where I'm really getting into the domain of modeling, integrating different types of data, heterogeneous data together, and for the domain of a little bit more larger than previously with oncology, but really to different problems in medicine to really go into let's say the larger subfield of precision medicine. So I'll try to explain this actually in the next few slides, because this basically heterogeneous data modeling refers to going more and more towards precision medicine, personalized treatments by combining the whole realm of data that we may have that could be available at a given time for a given patient. So it could be different types of data, obviously. Still, imaging is in the game, but can have a lot of different data sources, including also multi-omics data. So that's, let's say, the overall goal of my research at this time in Sherbrooke. And how does that translate? I'll explain it a little bit more precisely here with the description of my laboratory, research laboratory, which is called Medomics UDS. And why this name? Well, let me explain. Medomics actually is a consortium that started in 2019 while I was in San Francisco with my colleague Olivier Morin, and it regroups couple of centers at this time in different locations in the world. And what we're trying to do is act as a consortium, as a research consortium, and combine our expertise together for precision medicine. So the term Medomics comes from there, from the consortium. Then there's this branch of the consortium, which is my lab in Sherbrooke, that I call Medomics UDS. Now you know why my lab is called Medomics UDS. This is kind of the Sherbrooke logo with the Medomics logo. So now we can have can identify what that means here. That's my research laboratory, Medomics UDS. So at Medomics UDS, obviously I have different research teams. Sorry, I'm going to take a bit of water. There's three main teams, and in each team or research axis, I guess we're going into diving research in each of these, let's say, independent teams. So probably narrow, more deep and narrow research for each of these teams, which is still exploiting medical imaging for precision medicine, combining heterogeneous data together, modeling heterogeneous data together, and doing all of this in a federated learning context. And I'll explain a little bit what that means. But when you combine all of this, or when you explore, I guess, all of this, that's what I kind of estimate that when looking above all of this and exploring all of these themes, I guess it leads to being a researcher which does a bit more of surfing than diving, right? So let's say that's why I call this lab at this moment being 20-degree research. But there's a card in another card that we play here in this lab, and perhaps the game changer of our lab, which is a transversal theme, which is about the development of Medomics Lab, which is a platform for integrative data modeling in medicine. And I'll explain obviously what this is all about. And combining this transversal theme with all those different research teams that do deep and narrow research, I'm not exactly sure what kind of data that leads to, but we'll try to reflect on that, and I'll try to provide an estimate at the end of this talk. So let me explain now a little bit more in details. Again, all of this, the 3 different research teams, plus the transversal team Medomics Lab. Medical imaging, first team. So I previously showed type of study we could do, and that I did during my PhD, master and PhD at MPU, extracting imaging features from medical images. Here it's a sarcoma in the leg. We can do radiomics, extracting features with radiomics. We can do, obviously, use deep neural networks, convolutional neural networks, to build model, to do predictive modeling based on quantitative image analysis. That's still something I'm involved in. Different types of more, let's say, more specific projects. One example that I simply name here, analysis complexity. What does that mean? Let's say for different type of region of interest that we analyze. For example, here, tumor. As I said, there's different type of features we can extract. There's radiomics features, but volume feature is part of radiomics and can be useful for prognostication. Shape features can be useful as well. We can go more complex than traditional radiomics features by processing these images with different types of filters, more and more complex filters, and then afterwards still extracting features out of these filtered images. And basically we can, by going to the right of the spectrum of complexity, we get to deep learning, where the filters and the features themselves are learned for a given prediction task. So there's this spectrum of analysis complexity that we try to investigate and decide basically for different type of problems which level of complexity could be optimal to solve a given problem. So that's one example of the activities in this research team. Another example, more at the right of the spectrum with convolutional neural networks, is developing multitask CNNs. So what does that mean? Let's say for a given type of cancer, given problem, here it's renal masses, building predictive model for renal masses. So renal masses can be malignant or benign. If they're malignant, there could be different subtypes that have different aggressivity levels. And for a given subtype, the grade could be higher or lower. So how do we combine that, let's say, in one integrated model that basically uses what has been learned for the different subtasks, sorry. For example, the grade model should learn about should use what has been learned for the other task here, which is predicting malignancy, for example, or subtypes, where that leads to building multitask convolutional neural networks, where basically you have different networks for different tasks, but that are combined together. And that's a simple way of seeing it here, where parameters basically are shared between the different networks that perform different tasks. Different tasks, for example, whoops, sorry about that. Different tasks, for example, different tasks, for example, identify here, for example, as malignancy, subtype, or grade. So by combining those different networks together, doing multitask convolutional neural networks, the hypothesis is that by sharing information for the different tasks will improve the predicting abilities of the different tasks compared to if they were trained independently. That's another example for medical imaging. Going towards the other research team, which is heterogeneous data modeling. So research team 2. So the idea here is to exploit the different types of data available for a given problem, for a given prediction task in the realm with the goal of doing better precision medicine. So there could be overall, a lot of tabular data in the form of clinical or tabular data with different data tables, tabular tables. There's analysis of text note, which is also important. Images is a beast in itself. So how do we combine these things together in an integrated model? That's kind of the main objective here of this research team. There's multi-omics data also that can be integrated into this game. So there's obviously links between, let's say, genomic data and imaging data that can be exploited. There's obviously also links between what's written in the notes and what is seen in the images, and this can be also reflected in the EHR and the tabular data that we have. So how do we exploit the relations between the data and between the patients also? So that leads to different levels of graphical modeling. When I say between the patients, because we should perhaps not only base our prediction solely on our own set of features, but probably on the set of features, for example, of patients, for example, that are most alike us. So the idea here with this research team is to leverage multi-level graph neural networks for improved performance and interpretability. Graph neural networks basically are neural networks, but that exploit graphical analysis on top of it. So graphical analysis on top of it, in the sense that in a neural network, you can feed the features of a given observation, a given patient, one at a time into the network. Is going to give you an answer. But with graphs, the answer provided by the network is not just based on your own set of features, but on, for example, the set of features of your closest neighbors in one graph. So that can inform the prediction we're going to make for your own self. So there's connections between patients that can be exploited, connections between features that can be exploited. And when you combine all of these levels of connections, that create multi-level graphs, basically. So that's what we're trying to design in this specific research team here. One example that I can provide that for a study that we recently did is predicting late adverse effects. So the task here was predicting late adverse effects for survivors of leukemia. So for a child that survived leukemia years after, some of them, when they survive, some of them develop, unfortunately, late adverse effect. So how can we predict as soon as possible in the chain of treatment management that these patients affected by leukemia could develop late adverse effect based on the treatment, for example? So that was the main task, and the use case here is that we also exploited genomic data and combined it with different types of clinical data, building multi-level graphs, basically. Multi-level graphs exploit, so in some sense, in some way, to intelligently kind of connect the genomic information, which is embedded in our chromosomes. Our chromosomes can have different SNPs, single nucleotide polymorphisms. So different chromosomes can have different SNPs. So we try to build basically chromosomal graph that summarizes the SNP information on a given chromosome, and then combine the different information for each chromosome into an overall higher level genome graph, which was fed into a neural network, a graph neural network that also connected patients together. And that also integrated the information, the clinical feature information of the patients. So that was kind of an example of a design of a multi-level graph neural network here. So that's about it for research team 2. Now research team 3, which is about doing all of what I previously discussed, but in a federated learning way. Why federated learning? Because as you see here in this video, the idea is to leave the data where it is in the institutions and not transfer it to a central location, but rather transfer the models, right? Having the model, for example, a neural network travel from one institution to another and update itself based on the data seen in the different institutions. And that's how I strongly believe it will more fully exploit the potential of all the different data in Montreal, in Quebec, in Canada, in the world, basically, by building those federated learning studies. So building predictive models with federated learning, building predictive models such as multi-level graph neural networks with federated learning. So that's a challenge. And that's a challenge in terms of doing it all the way with this 20-degree vision. There needs to be 80-degree or more diving type of research done just for federated learning in the context of healthcare. For example, we're studying heterogeneity across institutions and how this could affect federated learning. What AI actually needs to detect when doing federated learning. For example, and I'll go quickly about this type of work we're doing that I like to call humble AI. Humble AI in the sense that when to detect when a given model built with AI should not be used, basically, on which type of patient or for which, on which type of patient that have a given perhaps profile different from the majority, that the model should not be used. And here there's a simple kind of view of what this means. Sorry about that. Meaning that, let's say, for example, we have data in 2 institutions, training data, and then testing data where we want to apply a model that we would have trained from institution 1. Here it's a scatter plot showing on the x-axis, for example, variable 1 for the patients, and on the y-axis, variable 2. So it's a scatter plot in 2D where there would be something to predict or to differentiate between class 1 and class 2 and class 0. So we notice that in the training data, for example, there seems to be just like one patient population where we could draw a line and build a model that basically have a kind of a good performance for discriminating between class 0 and class 1. Let's say we get into another institution in this federated learning context where there seems to be kind of a hidden or another patient population that we may not have, that we may not be aware of, basically, when we gather all of our data from one institutions to be applied for a given model that was trained, and that we may not be aware that this patient subpopulations with a different profile should not be used for the application of this model. Well, we're trying to develop methods to detect this heterogeneity, and it can be simple, but it can be more difficult than we think to do that in high-dimensional spaces. This is 2D, but let's say we have a model with 100 features. It kind of becomes more complicated. So we're trying to detect automatically, basically, these patients' populations for which a given model should not be used, for example, in the federated learning context. That was one example. Another example of our activities in terms of federated learning, that's the example one was really about more, I would call it more theoretical, and that can be done with simulations, basically with our own set of data. But the idea is to do that in the real world, right? Federated learning studies. We're trying to contribute as much as possible to real world studies. Recently, our lab was part of this, what I call this tremendous tour de force, or gigantic study that UPenn in the US they led and that they carried out, and that was published just last month, where they combined, basically, they did a real world federated study with 71 different sites in the world, including McGill, 71 different sites in the world. That must have been really a huge management challenge. And But because they managed to combine data from so many places and increase basically the number of patients that could be included in that study, to build a model here that was specifically to segment tumor subregions in glioblastoma. Because they were able to increase this number of patients available to build a model, which was only possible by doing a federated learning study, that we could not have thought of combining the data from all these different places in one central location in a reasonable time frame. So because they did that, they were able to show that by enabling federated learning in the real world, they got 32% improvement in the accuracy of segmentation of 3 different tumor subregions in the glioblastoma. So that was great, and that's the usefulness of federated learning. So that's basically it for research team number 3. And as I discussed before, there's Medomix Lab coming in, but let's say I try to show this vision or the integration of the 3 different research teams into one overall vision. I would show it as is, and at this time I still find that it's really pretty much surfing research, trying to combine all of these concepts together, basically, meaning getting the best out of all those different types of data, the best out of notes analysis, text notes analysis, the best out of imaging analyses, multi-omics analyses, combining these data together into multi-level graph neural networks, into first a graph at the patient level where we get the best graph emitting or patient or representation of features for one patient, but then how do you combine the representation of those different patients together into a higher level graph neural network connecting patients together, and do that into a federated learning way? That's basically the whole challenge and the whole vision of our research, doing all of this, putting all of this together here. But and then there are research, let's say, improvements done, or really, let's say, a lot of diving research in different spots here of this picture. So how do we combine the diving research, kind of the more deep research done in different parts of all of this picture here, combine it such that we can put them all together first and be able to carry out a given study with all those different tools all together in one smooth platform. I guess that's why we're developing this thing here that is called Medomix Lab, and that's why Medomix Lab comes in to help here, is to be able to use all the different research improvements done in all those different aspects here of this vision. So there's Medomix Lab that we're trying to develop. As I said, that's our transversal thing, combining the research developments into one integrated platform. And I'm happy to say that it's supported by a Unité de soutien Système Centré Apprenant du Québec. So that's good. So what is it, Medomix Lab? Basically, as I said, it's trying to combine all the different research developments in the different themes of our research. Basically, it consists of 5 different modules. I won't go too much in details, but we've figured that we need basically 5 higher level modules to do end-to-end studies in the domain of precision medicine. One input module to integrate all the different data types together and get some representation of this data, do quality assurance of this data, basically be able to visualize what we have in hand for all the different data types, be able to extract features out of this data for text with an LP or with radiomics, convolutional neural networks for imaging, for example. Discovery module, where it's more about statistical analyses done with all those different data types. And the core is really about the learning module, where we have the opportunity to test different experimental design. Which type of data am I gonna combine with the other? Am I gonna use text plus imaging, or trying to estimate if the tabular data, for example, is useful for a given problem? That's where we can design, basically test multiple hypotheses and design different experiments, and do the hard work of machine learning. And application module, which goes towards model deployment. Basically, once a model is built, how do we, in which form do we put it to really be deployed in the real world? So one other concept which is important in this transversal theme and in this platform is the user versus developer experience. We want this to be useful enough for developers to integrate, as I said, new capabilities into it, new research developments into it. And that's a challenge, to make it as modular as possible, so that new research developments can be integrated in each of these different research modules. What you can think of here is having modular Python code, including state-of-the-art packages that already exist in machine learning, like PyCaret, CRCHUS, which combine basically scikit-learn and PyTorch, Flower for federated learning. So there exists already nice packages, but how can we make them work together? That's a challenge, and that's what we're trying to do, basically. And we have sets of demo tutorials to get into this platform, active GitHub repo, rich documentation. So everything you really need for on the developer side, that we're trying to put it there. But then on the user front, we also need we can get around with having some interface to be able to work better with all those different models into an integrated platform and an interface, basically, that allows you to navigate between all of this. One example that I can show you, basically, that we're trying to build this platform based on the DrawFlow library. So DrawFlow allows you to do exactly what is shown right now: connect boxes together and build pipelines for a given project. Here, the example is about the extraction module, where we're doing at this time radiomix analysis. Radiomix analysis for a given patient. If I go back just a little bit, radiomix analysis for a given scan with a given segmentation box, and for different types of processing and different types of feature extraction. So the idea here is that we build a pipeline here. We're building a pipeline connecting box together. But processing is a whole, there's different sub-processes into this box that can go into this box. So the idea is to be able also to go into different, build sub-pipelines for a higher level pipeline. Just like here, it's the pipeline for processing that is shown, where we do interpolation, segmentation, a radiomix process, ROI extraction, and so on. So that's building the processing pipeline. Then we go on and we do, for example, feature extraction after segmentation, processing, extraction. But extraction also can have its pipeline, its own pipeline, where we can decide for example, to extract different features for a given pipeline. So the whole idea also is to be able to visualize as we go along how the images have been modified as we go through the different pipelines, after segmentation, after processing, after filtering. So at each step in the pipeline, we're able to stop and see what has become of our images, for example. And here, I think the most important part is, with this pipeline strategy, you can do exactly that. Create different pipelines where for the same segmentation, we'll have perhaps different processing and different extraction. So there's two pipelines here, different processing, different extraction created in two pipelines. And if we continue, well, we can run all and ultimately get our radiomix features, for example, for the two different pipelines. That's the idea of having of having this user experience, I believe, connected as much as possible to the developer experience here. So that's the strategy that we're developing right now for Medomics Lab. Let me talk quickly about different research networks evolving around our research laboratory, or more likely the inverse. We are revolving around in these networks, which is the IBSI and Réseau Santé Numérique du CRCHUS. Let me just quickly give a word about that. So our lab is involved into this initiative, Image Biomarker Standardization Initiative. If you do radiomics, I advise you to go through this standardization tests, benchmarks that have been defined by the IBSI. So really an international group of researchers trying to standardize radiomics calculations, and it's on the track to be established as international research standards. So I think that's really important in the domain of radiomics, and it's really diving research in terms of radiomics here, theta of 80 degrees, if I may put it that way. But it's one example of the networks with which we collaborate. And let me say a few words about Réseau Santé Numérique. If you're interested, there's this competition. The CRCHUS is renewing basically the research networks in Quebec, this competition, which will happen on April 23. So we're building basically the network at this time. If you're interested in this network, it's a transversal network, Réseau Santé Numérique, digital health. And the governance we're thinking of is having 4 co-directors, and that's actually being set up. 4 co-directors, one from Laval, one from UDM, one from UDS, one from McGill, 8 co-leaders divided equally into the different universities. And we want to have also co-leaders of transversal teams. And let me discuss a bit quickly about those transversal teams. Basically, we're missing some leaders of the transversal team. So I take this opportunity to inform you about this Réseau Santé Numérique that we're building right now. We're missing co-leaders of transversal teams. At this time, we have more than 100 members that wants to join this network. So that's great. And the goal, if I can put it in the context of this diving versus surfing research, is to do diving and surfing into this network, right? Spanning the whole spectrum of theta from 0 to 90 degrees, because that's what the network is all about. Connect divers together and surfers together to span this whole realm of diving versus surfing research. That's basically what a network is all about. And how we plan to do this is really by being really a transversal research network, and partnership with other networks that may be doing more diving research in the sense that they are targeting more specific research subjects. Well, we think we could be the glue between the different research networks in Quebec to and help to provide different developments in the digital health science, such as AI4Health, for example. And there's different transversal themes, obviously, that we're thinking of, such as training, interdisciplinary training between the different research axes, ethics, data management, harmonizing methods, rights and policies, regulations, basically. So there's a lot going on, which is transversal in these research axes, and that's what we're trying to develop. So if you're interested, do not hesitate to contact me if you want to have more information about the upcoming, I hope, Réseau Santé Numérique. So to conclude all of this, let me say this final word. So I tried as best as possible to tell you my academic journey before 2020, where I was at the MPU, and during the last 3 years while I was at Sherbrooke, and in which I estimate to have done more surfing research than diving research, right? In the future, I plan to let's say continue these developments, obviously in terms of heterogeneous data modeling, but really going a bit more further trying to develop something more in terms of continual federated learning in healthcare, being able to have these types of models that continuously update themselves in different federated learning networks. And that's, I would say, kind of going a little bit more further towards the analysis side. We want to get better going towards the data side of the spectrum, if I may put it that way, and be able to better connect the different types of data together with medical ontologies. Really a requirement to allow real-world federated learning studies. And I plan to continue interdisciplinary correlations with Middlemix Lab, this platform, really important component of our research. So I'd like to say that, of course, we're actively recruiting students, hiring research professionals, and trying to build new collaborations in different areas of medicine, in oncology, and trying to solve different types of problems in medicine. So please feel free to contact me if that interests you. And to finish all of this, going from 80-degree research during the PhD to a bit more towards surfing research in the last 3 years to really try to consolidate some type of research vision in the future, as you can imagine, and as perhaps you have guessed it, I will try to become really a real 45-degree research guy. That's my plan.